So this is the third and final lecture for Chapter 5. So we'll start here with Fisher projections. This is another way to represent chemical structures. This is very commonly used in biochemistry, the smaller molecules in biochemistry, and so we cover it here, but we're not going to go into it in great depth, except I will make a few points about it so that you won't become confused about it. So in the Fisher projections, the horizontal lines represent attachments coming out at you. So the lines that are going across, you should regard those as being wedged out. Lines that are vertical, going up and down, you should regard those as being wedged back into the page. But you only draw the line. So this drawing is equivalent to that drawing. Fisher projections are useful when drawing molecules having multiple chirality centers. Like here, this has two centers of chirality, 3 chiral centers, 4 chiral centers. And so it was sort of developed for use with sugars. Notice that when it is used for compounds like sugars, the carbonyl group is always positioned at the top. The CO double bond is always at the top. It's not at the bottom. Okay, and so then when the nomenclature is used, typically the nomenclature will apply to this chiral carbon, the very bottom chiral carbon, on the molecule with the carbonyl group at the top. The bottom carbon at the of the molecule, the one farthest away from the carbonyl. But you put the carbonyl at the top, and then you go down the chain to the last chiral carbon. That's all I'll say about that in naming using the Fisher projections. So they're useful to assess stereoisomeric relationships, so you can see that these compounds with R1 and R2 different are enantiomers. Here, these are diastereomers. Okay, that's easy to see. They are not mirror images, but still stereoisomers. This can get a little bit confusing. Remember, conformers are not isomers. And so these conformations, you could say that they're chiral, and you could say that they're enantiomeric, but for practical purposes, they will not be, because this rotation about the carbon-carbon single bond is occurring so rapidly that it will be impossible to make any use of any isomeric relationships. This rotation, this interconversion is just happening too fast to make any isomeric relationships useful. So these are regarded as conformers and not isomers. So this compound is not regarded as chiral. The same way with the cyclohexanes. This compound is not regarded as chiral because the interconversion is just taking place too fast. You could draw them and look at them and say, yes, this should be enantiomeric. If there was a way to freeze out this interconversion, it could be regarded that way, but the interconversion is just happening too fast. Here, this has an internal plane of symmetry, and so it would be its own mirror image. So this would be a meso compound anyway. You can also have chirality without a chiral center. So in this case, here, so we don't cover this too much in this course, but it's just touched upon, just so that you'll know that this exists. What happens is normally you would have free rotation about this carbon-carbon single bond. You can see the arrow in here indicating free rotation about that carbon-carbon single bond, but it does not happen because of these bulky groups. This is diphenylphosphine here, diphenylphosphine, groups, and they are just too huge to be able to get by each other. And so it can get stuck at in this conformation or this conformation. And so for practical purposes, these do exist as two different isomers. You have to heat these up to be able to interconvert them. Heat them up to be able to get the rotation about the carbon-carbon single bond. And so these are chiral compounds, even though they don't have a chiral center. They get stuck in one isomer or the other because of the steric hindrance here. Steric hindrance to the free rotation that would normally occur about that carbon-carbon single bond. Allenes do not have a chiral center. I guess, well, they don't have a chiral carbon. I guess their center of chirality would be right here at that carbon, but it's not a chiral carbon. So they can be chiral, you can see here, so they have a mirror plane. These are two enantiomers for allene, and I'll make a model of that and let you see it in the other film that I'm about to make. So resolution of enantiomers, this can be important. Most methods of separating compounds from one another take advantage of the different physical properties. As you know, the enantiomers don't have different physical properties. So typically the only way of even distinguishing between the two is looking at their optical activity. So let's look at some ways that have been used to separate the compounds, because without different physical property, it becomes difficult. So Pasteur actually was the first one to do this, and the way it happened is he, back in these days, 1850, I mean, that's 170 years ago, they did a lot of just looking at compounds. They would synthesize compounds and look at them under the microscope or look at them using a magnifying lens. And so he was looking, he had made this compound just with typical starting materials. He wasn't starting with one optical isomer or another. They knew by this time that optical isomers existed because they had been able to get compounds from nature and put them in the polarimeter, and they knew about this property of rotating plane of polarization of polarized light. But they did not know really, where it came from. They did not know how to synthesize those compounds. And so when he did this, it was really a revelation. So he made this compound, and this compound existed as crystals, enantiomeric crystals. And notice it's a salt. It's a disalt, actually. It's a dianion, the salt of sodium and ammonium. So, cations. And so he had both of these in the salt. Okay, and he was looking at them using a magnifying glass, and he was astonished to see that the crystals appeared to be, these were rather large crystals, and they appeared to be mirror images of each other. The actual crystals were mirror images of each other. So he had a mixture of crystals that were mirror images of each other. So he pulled out his tweezers and very patiently sorted those crystals into two piles, which, the piles were mirror images of each other. So they were, pure. Each pile was pure, but they were mirror images of each other. And then when he dissolved those and created a solution of each and put them in the polarimeter, he realized that they were optically active. They rotated the plane of polarization of polarized light in opposite directions. And so this was the first separation. And so this is called a mechanical separation because they simply got out the tweezers and separated the crystals. And it's very unusual for this to actually succeed, okay? Usually the crystals are not mirror images of each other. So, just the fact that he happened to be looking at this one, and this one crystal did have that characteristic, it's just luck that it happened. Who knows how many times you'd have to look at crystals under a magnifying glass to be able to see that, but it happened. And so he reported that. I think I skipped one. There we go. Okay, and so another method that can be used is to convert your enantiomers into diastereomers. So here, these are mirror images of each other. This is a pair of enantiomers. And when this solution, which is a solution of the two enantiomers, when that is reacted with this compound, you get this. So this acid simply donates simply protonates the ammonia, and once again, it will create this salt. And here, these two pieces are the same. These two pieces are mirror images. And so this is a diastereomer. Okay? This is a diastereomer of that. It's not a mirror image, but it's not the same. They are not the same. And so diastereomers do have or can have different physical characteristics, and these can be separated. Often they're so similar that it's difficult to separate them, but it can be done. And so they can be crystallized differently. One can crystallize at a different temperature than the other, or one can crystallize from a solvent that is not the same ratio of typical solvents as each other. You can use solvents which are different, have different ratios of different compounds, and one will crystallize out and the other one will be left in solution. So there are different tricks that can be played, and you can play tricks with raising or lowering the temperature in solution, and one crystallizing out and the other one being kept in solution. So this is to form a diastereomeric salt, a pair of diastereomeric salts, and separate those somehow on some physical characteristic, based on some physical characteristic. And then this third way is by using chromatography, and this can be gas or liquid chromatography. And so here, what you have, it's sort of similar to what we saw on the previous slide, in that you'll have a pair of enantiomers in your sample. And you may or may not know how chromatography works, but you have an inert, let's say, solid, and on that inert solid, there will be coated on that inert solid a compound that is that has an affinity for your sample, for your enantiomers. Okay, but if the compound that is coated on the solid in your chromatography tube, it will have an affinity for one of your enantiomers more than the other one. So if it is optically active, if that compound that is coating the solid, the active compound on the inert solid inside the chromatography column, if it is optically active, it will have a greater affinity for one of your enantiomers than the other one. And so you can think of it as sort of, once again, you know, a right-handed person going down through a crowd of people. Think of it as a right-handed person going down through a crowd of people and shaking hands with people who use their right hands to shake. And so, and the others are, say, left-handed, and they don't shake hands with their right hands. They shake hands with their left hand. Well, the one will stop and like interact, shake hands, you know, and spend a long time going through the crowd because it's interacting a lot with the phase that's on the inert solid. But the other enantiomer will just go right through because it will not interact at all or interact as much with the coating on your inert solid. And so you can think of it as just, you know, one passes through slowly because it's interacting a great deal, and the other one passes through rapidly because it's not interacting. And so you can separate them by gas chromatography or by liquid chromatography. One will come out faster than the other because it just doesn't interact with whatever it is that's coated on the solid phase. And so I hope that helps you understand a little bit better. So let's look at E and Z designations used in nomenclature for alkenes. So let's say that you have an alkene. We've been looking at alkenes where you would have only di-substituted alkenes. So you would have a hydrogen, a CH bond, and a CH bond, one on each end. And here is an example where it's a tri-substituted alkene. Or you could have a tetra-substituted alkene. And so what do you use? You can't use cis and trans because you don't have CH bonds on each end, a CH bond on each end. And so cis and trans can't be used in this situation. And so what we have to do is use that Kohn-Ingold-Prelog rule again and figure out which one takes precedence on this end. And so it's going to be fluorine versus carbon. Fluorine has a higher priority. Here you're going to have nitrogen versus hydrogen. Nitrogen has higher priority. So the higher priority groups are on the same side here. So this has the higher priority groups on the same side. This one has the higher priority groups on opposite sides. And so I think this is identified on the next, yes. So fluorine has higher priority here. Nitrogen has higher priority here. And so we're going to use E and Z. And so if the higher priority groups are on the same side, it's said to be Z. If they are across from each other, it's said to be E. So let's look at the next slide. There we go. So Z is for zusammen. That's a German word which means together. However, in Germany, they have several different words that mean together. And so it's interesting that the word zusammen was selected to describe this because I took scientific German. And the way it was described to me is that the word zusammen, which means together, was selected to describe the interaction of these two groups that are on the same side. Because my instructor told me that zusammen is a word that might be used to describe two lovers walking alongside the river, you know, touching, bumping, rubbing against each other. And so that's to reflect these two groups that are so close to each other that they're constantly interacting, touching, rubbing, bumping against each other. So there's some steric interaction going on there, which is reflected in this word zusammen, which means together. Here. And the word entgegen means opposite, on opposite sides. So this is sort of similar to the word trans, across, but here entgegen means opposite in German. So they're on opposite sides of the double bond. Here this would be similar to cis, except we don't have two CH bonds. We have only one, so we have to use zusammen, abbreviated Z. Here we're using entgegen. This is abbreviated E. And so that takes care of chapter 5. So that's the end of the discussion, and I will make your video of the molecular models, and then I'll post these for you, and I hope they help.